I'll structure the talk as follows. So first we'll have a high-level overview. I'll talk about the introduction of the Internet computer, then how to integrate the Internet computer with Bitcoin on a high level. Next comes the more technical part. First of all, talking about the Internet computer protocol, giving you an idea of how it works, and then the technical architecture of how Bitcoin integrates into this protocol stack. And then I'll conclude with some key takeaway points and an outlook. Now the first part, and let's talk about the Internet computer. There have been three great blockchain revolutions so far. The first one was Bitcoin. Bitcoin showed the world that it's possible to build a completely decentralized ledger which is secure and you don't need to trust any central party. That was a revolution. However, it's just a ledger and you can't run arbitrary code in it. Vitalik Buterin later launched Ethereum, the second blockchain revolution. Ethereum allows you to run arbitrary code on the blockchain with the same trust assumption that Bitcoin has. This was the second revolution. Smart contracts were born. The third big revolution is the Internet computer. The Internet computer completely reconsiders how to build a secure distributed system based on blockchain technology. A system which is extremely efficient, a system which is limitless in terms of its scalability, a system which provides a nice developer experience, rich language support, and a system which has a novel governance approach. The Internet computer. The foundation of the Internet computer are data centers and node machines running in those data centers. The node machines are connected through the public internet. The node machines run the Internet Computer Protocol, ICP. And running the ICP on the nodes creates the Internet computer. The Internet computer resides in public cyberspace. It's not located anywhere. It's a virtual supercomputer, if you will. And people can deploy smart contracts, we call them CANISTERs or CANISTER smart contracts, on this public cyberspace, or if you will, directly on the internet or this extension of the internet. And users can interact with the Internet computer by sending messages to CANISTERs, and CANISTERs can send messages to other CANISTERs. And the Internet computer is secure, fault-tolerant, and scalable. So what's a CANISTER? A CANISTER smart contract. It's an advanced form of smart contract. It comprises two things: WebAssembly bytecode, the instructions, and memory pages, the state of the canister. Both together form the canister. They're encapsulated secure units. And what's special about it? It's very powerful. It's powerful in the sense that canisters can, for example, serve the complete user interface, the web page from the blockchain. You don't need big text cloud services anymore, which of course strengthens the trust model of smart contracts served by the Internet computer. Furthermore, users don't need gas or tokens in order to interact with canisters, so it makes it much simpler. Also, we have a very nice user interface, user experience in terms of how users authenticate. They can use biometric authentication based on WebAuthn using our Internet identity system. And canisters can scale up very well. So a single canister can consume tens or hundreds of gigabytes of memory if you want. So you can build scalable services. Also, in terms of language support, we support a plethora of languages. So essentially, any language that compiles to WebAssembly can be used to write smart contracts for the Internet computer. We have two languages for which we offer a rich SDK. This is Rust, you all know it, I guess, and Modoko. Modoko is a language specifically crafted to be aligned with the features of the Internet computer and extremely easy to learn. So next, let's look at what the Internet computer is built up of. So it's subnets or subnetworks. Let's look under the hood of a subnet. So a subnet is built up from node machines. Those node machines are located throughout the globe. So the idea is to achieve decentralization. So we decentralize as much as possible in an algorithmic way. And there are four dimensions of decentralization. So first of all, choosing nodes from independent node providers. Having these nodes located in independent data centers. Number three, having the data centers in different countries or geographies. And number four, having the countries in different jurisdictions. This helps to achieve best possible decentralization. And this forms the basis of the basic level of decentralization, so a decentralized compute platform. And it's secure, it's fault tolerant. which is achieved by replication. Essentially, each subnet is a replicated state machine. Each node or each replica performs the same computations on the same messages. And this is done through consensus. So each of those subnetworks is its own blockchain and progresses at its own pace and can communicate with other subnetworks. Now let's look at how we scale up, because if you just have one subnetwork, it's rather an internet calculator, not an internet computer. In order to reach the real internet computer, the big scalable thing, we need many subnetworks. In the future, we want to have tens or hundreds of thousands of subnetworks to scale up as we want. And canisters now can communicate not just with canisters on the same, but also canisters on different subnetworks. And this makes it easy to build scale-out architectures with the canisters. So something similar, what you can do on public cloud, but it's not public cloud, it's a secure blockchain-based system which scales like the public cloud. So it's a completely novel approach to secure blockchain, scalable secure blockchain. So next, let's look at the governance. We also have a new approach of how we do governance. So the idea is that we have so-called NNS, the network nervous system. It lives on a special subnet, and it has special privileges to control the internet computer. And now there's a governance token we use, the ICP token, Internet Computer Protocol token, and token holders can vote using this token. And this voting determines what we do with the internet computer, what this NNS network does. So there is a more operational area of governance. So the NNS controls all the subnets. For example, it decides which node gets added to which subnet, can remove nodes from subnets, it can update the replicas. All of those things are controlled by the NNS. And there's the more strategic aspect to the governance, which is how the internet computer protocol and the whole internet computer evolves at large. So this is done by, for example, motion proposals. We, or anybody, can launch motion proposals, which are voted on by the NNS. And this determines which items, which roadmap items we will work on and which we won't work on. So this is governance by the community. So the big goal is that our community, the internet computer community, decides what happens with the internet computer, what we build, what we don't build, how the protocol evolves. And we are more and more trying to push this responsibility to the community with this voting on this system. One good example is the Bitcoin thing I'm talking about now. It has been voted on by the community. It has been discussed extensively in the forums, so we've gotten requirements from people who want to build on this feature. And what we're also doing, like next week, we have an upcoming developer workshop where we talk to some of the developers that already have ideas what they want to build with this Bitcoin integration. So it's pretty exciting to work with the community so closely, and we try to intensify this in order to decentralize further. So this was a rough introduction to the internet computer. Let's next talk about the integration with Bitcoin at the high level still. So Bitcoin, the world's digital value store, digital gold. Bitcoin is based on the UTXO accounting model. It means transactions generate UTXOs, unspent transaction outputs. Those can get consumed in new transactions once and create new transaction outputs. A UTXO is essentially a coin. Now let's look at the transaction. The transaction is built up from UTXOs that are outputs of old transactions that have been spent yet. Then we define whom the new UTXO should go to, for example, to Bob in this case. And then Alice, in this case, needs to sign the UTXOs she owns in order to unlock them and prove she's the holder and protect the integrity of the transaction. If that's done, transaction is finalized, finished, it can be sent to the Bitcoin network. It gets mined into a block. Then the block goes onto the blockchain at some point. And then there's further blocks coming on top. There's a proof of work mechanism. We wait a little bit in order that we can be sure that there's no other chain where other transactions are in, and then we can be assured that this transaction is valid. So that's roughly how Bitcoin works, and I used it for introducing the visual notation to the use later. So now, integrating the internet computer with Bitcoin. What are the goals? First of all, web speed smart contracts for Bitcoin. Second, we want a direct integration, which means no intermediaries, no bridges. This is unique. No one has done that before. It means less risk for Bitcoin holders. And the developer experience, which is easy to use APIs. You can easily get started doing Bitcoin work on the internet computer. And of course, a great experience for the end user, which comes out of the box because of using internet computer smart contracts, internet identity, all of those things. We get this for free. Now, there are two challenges. The first one is canisters need to be able to hold and receive Bitcoin directly on the Bitcoin network without intermediaries. And second, canisters need to be able to transfer Bitcoin out to other canisters or users. And if we solve those two challenges, we have a very powerful framework to have one blockchain directly integrate with another blockchain and use the one tokens on one blockchain on the other one. So it's very powerful without any intermediaries, which makes it, of course, more secure and gives it a very slick trust mode. Let's look at this, how it's done at a high level. So with the internet computer, a couple of notes of the Bitcoin network. First of all, direct integration means no intermediaries between here, as you already said. Less risk for the Bitcoin holder. We had lots of breaches of intermediaries like bridges and hacks where millions of dollars in Bitcoin and other currencies got lost over the recent years. Can't happen here because there are no intermediaries. So what does it mean for us? First of all, we need to now look at the challenges we have. So canisters can receive and hold Bitcoin. How do we achieve that? The canister needs a public key. We use ECDSA. So the public key needs to be generated somehow. We extend our protocol stack here with a threshold ECDSA scheme. I'll talk a bit more about this shortly. And the canister can obtain a public key from here. Then the canister can obtain arbitrarily many public keys using standard FIT32 key derivation. These public keys can be used to create Bitcoin addresses to which transactions can be made. So that's the first part, receiving and holding Bitcoin. It's passive on the internet computer to actually receive Bitcoin. The sending is now the active thing. So canisters, second challenge, canisters can now transfer also Bitcoin out. This requires a couple of things. So first of all, we need to get the UTXOs that the canister holds. How do we do that? So we build another extension to the protocol stack, this Bitcoin extension here. And then we need to do the following. We need to get somehow Bitcoin blocks into the internet computer. So we connect in a decentralized manner from many node machines. So essentially all the node machines in the subnet that is Bitcoin enabled connect to multiple Bitcoin nodes and pull in Bitcoin blocks. Those blocks get processed in terms of extracting the UTXO in the blocks and keeping it in the state of the internet computer. And then we can serve UTXO queries to canisters. So canisters can ask which UTXOs are available for a given Bitcoin address and get the response. Now, based on this, we can build up transactions. So we can build a transaction based on the UTXOs. This is quite simple, normal coding. We can define whom the new UTXO should go to. Now, the complicated part is we need to sign this transaction. So we need some kind of appropriate signature mechanism. This signature mechanism is threshold ECDSA signatures. The reason is that we are a decentralized system with a trust assumption that up to strictly less than 1/3 of the nodes can be arbitrarily faulty, which means we can nowhere store the private key in its entirety, which means we secret share the private keys. The private key is stored in a secret shared manner among all the replicas. It's never ever reconstructed, not during key generation, not during signature generation, never. It never exists as a private key, it exists as private key shares among all the replicas. It could be 50 replicas, 100, 150, 20, whatever, depending on the subnet selection. And now, if we want the signature, the canister asks the subnet to generate the signature on its behalf. The subnet then performs cryptographic multi-party computation to compute based on the signature shares without reconstructing the private key, an ECDSA signature on the message. These ECDSA signatures can be used by the canister to finish up the Bitcoin transaction, put the signatures in, and then submit the Bitcoin transaction with an API to the Bitcoin component here, and then it can be submitted out to the Bitcoin network through all the connected nodes. So it's very quickly disseminated to the Bitcoin network. So that's a rough high-level overview of how the integration works. Without intermediaries, this is something that hasn't been done before. The internet computer can do it because of some of the powerful features it has.
Can I ask a question there? You're still bound by the transaction speeds and transaction fee of Bitcoin.
The transaction fee is applied regularly, of course. Yeah, it's like a user makes a transaction, yes.
So it's the same as on the Bitcoin network?
Yeah, so it's like when you're doing a transaction as a user. So it's just a regular transaction. It's just done in a decentralized way.
So you will do it then later, because when I think of internet computer, I think about a lot of transactions very quickly, usability, etc.
So you can have wrapped Bitcoin on the internet computer, which is one application of this stuff. Then you can have transaction finality in 2 seconds, just doing wrapped Bitcoin transactions in a canister on an exchange. Then you do clearing transactions in a batch with the Bitcoin network.
But you're basically competing with the Lightning Network now?
Competing, I mean, this is one application you can do. I mean, we could see it that way, yes. But this is just one application, we can do much more. So now, what does it mean to bring web speed smart contracts to Bitcoin? So first of all, we can bring some of Bitcoin's liquidity to applications on the internet computer. We can build smart contracts with a great user experience, like easy authentication, for example. Users authenticate using the web authn protocol, passwordless, it's sorted on all major platforms, and on the mainstream platforms, you can do biometric authentication, which is really nice. No passwords anymore, easy authentication to the smart contract. Furthermore, you don't need to pay gas fees, also very convenient as an end user. And what this all gives us immediately is that we have the possibility of building or having a Bitcoin wallet in a decentralized fashion on the internet computer. You never touch a Bitcoin key, you don't need to trust a single party, still you have a Bitcoin wallet. So it's a very powerful feature. And this feature can be used in any smart contract you build on an internet computer. So it comes with every canister, you can just use this API, which is also very nice. So what we do is we lay this technical foundation that every canister can use Bitcoin in a very generic manner. And some application scenarios we can think of are something like directly wrapped Bitcoin, like wrapping Bitcoin without an intermediary party, very powerful, much more secure than wrapped Bitcoin with intermediaries. Let's call it ICPTC. Or we can do decentralized ICP-BTC exchanges, or buying NFTs with Bitcoin, or things like topping up canisters with Bitcoin, so paying for the computations as a developer. And there's lots of more things you can think of. I think your imagination is the only limitation here. So next, let's look at the Internet Computer Protocol stack in somewhat more detail. So this now starts part 2, this somewhat more technical part of the presentation. So the protocol stack is comprised of 4 layers. The lower 2 layers are responsible for message acquisition and message ordering, which means every replica on the subnet agrees at the end of a round on one intercomputer block or IC block containing messages, and it's all the same block on every replica. And this block is given up to the upper layer and is getting executed in a deterministic fashion. That's exactly what's required for deterministically executing the state machine, obtaining a replicated state machine and obtaining this secure blockchain-based distributed system. So that's now, so essentially what happens is in every round we have a state transition from a previous version of a state using one block, the same block every replica, getting to a new version of the state, and the same one on every replica. So now let's look at the protocol stack with somewhat more detail. So at the lower layer, let's say a user submits to one replica an ingress message to interact with the internet computer. Could be some form of transaction. This gets broadcast to all the nodes of the subnet. And other transactions come in as well, so there's a pool of transactions in the end. Now what we need to do is we need to build an IC block, which then can get to deterministic execution in the round. How this is done is by a multi-stage consensus protocol. Consensus in the internet computer is designed in a way to be very high throughput, so 1 block per second, and very low latency, so with finality time of 2 seconds if the subnetwork behaves well, and it can go up a bit if there's lots of malicious activity, like network attacks or dishonest replicas. Now there's 3 stages. There's block making, notarization, and finalization. Let's start with block making. So block making means block one of the replicas or multiple. So if we need multiple, if there's dishonest behavior, in the ideal case we have only one. Let's now look at this one. So we have block maker that pulls ingress messages into a block, and it also pulls messages from other subnets. That's exactly the cross-subnet communication that I've talked about. And then it proposes a block by putting it into the artifact pool and having it broadcast to all the replicas of the subnet. And this proposal of a block is now picked up by every replica, acting as a notarizer, or a notary. The notarization has the goal of the subnet agreeing on valid blocks. Agreement means at least 2/3 of the replicas agree that the block is valid. How does it work? A notarizer issues multi-signature shares on blocks that it deems valid. A valid block is one where the signatures on the messages validate. So it issues such notary signature shares. Those get broadcast to all the nodes on the subnet, and it also receives signature shares from other nodes of the subnet. And based on the blocks that it has seen in a round, and also all the signature shares it has seen on the round, it decides whether it will sign a given block. And also based on how far the time has progressed within the round. But I can't go into all the details. The goal here is to produce as few blocks as possible in a round, because this makes finalization easier, but as many as needed, at least one. Now if you have at least one fully notarized block, so one that has at least 2/3 of the replicas behind it, we can go towards finalization. Finalization works also with the finalizer. So every replica acts as a finalizer. The finalizer pulls in received fully notarized block. And in case this replica has not notary signed a different block in this round, then it signs this given block and broadcasts the share again and receives shares from others. And exactly using this rule, we can prove that if there is a block that receives finality signature shares from at least 2/3 of the replicas in the subnet, then there is only one block. Of course, it can happen that there is no finalized block in a round, then finalization can happen a round or a couple of rounds later. This again happens if there is malicious behavior going on. I can't give the details, you can read up on this. It's an extremely efficient protocol built to have low latency for blocks, so low finality time and high throughput. Now, all of this is powered by what we call chain key cryptography. So things like BLS threshold signatures, non-interactive distributed key generation for those, BLS multi-signatures, so a large toolbox of rather advanced cryptographic protocols that are used to power those protocols. So it's not only in this layer, I just mentioned those. This chain key cryptography is mentioned, is used on all layers of the internet computer. So next, let's look at what happens with the finalized block. As I said before, it's the same finalized block on all the replicas of the subnet, and this is now passed up to the upper protocol stack layers. And there's a deterministic execution happening. So first, all the messages are extracted from the block, going into the induction pool, which is essentially all the queues, input queues of the canisters, and then they get scheduled for execution. So the message scheduler essentially calls the canister code in the hypervisor, which executes the WebAssembly instructions based with the inputs. And the returns can be responses or can be calls of other canisters, which could be scheduled again in the induction pool, or it could be responses or other canister calls, which would go to subnet, to queues, to other subnets, which again provides responses or cross-canister calls to other subnets. And those would then be pulled by block makers on other subnets, much like we pulled without block maker from other subnets in the beginning. So this explains how the cross-subnet communication works in terms of the protocol stack. So this was a very high-level introduction to the protocol stack. Just to give you a rough overview, then use it as a basis to show how we integrated Bitcoin here. We walk through again. Sorry. So now let's look at the technical architecture of the Bitcoin integration. So again, let's look at the product stack, but this time with Bitcoin and threshold EasyDSA functionalities enabled. We're also still at a high level, but a bit more technical. We have the same diagram with a couple of Bitcoin nodes usually waiting for the integration. Now what we needed to do is the following. We need to build a BTC system component. This implements the bulk of the Bitcoin processing logic. It offers an API, on the one hand, getting a UTXO set for Bitcoin addresses, which I mentioned earlier, and also something for submitting transactions to the Bitcoin network. At the networking layer, we have a couple of new components as well. So we have a Bitcoin adapter, most notably. This implements the bulk of the Bitcoin-related functionality at the networking layer. We have a networking transit, which is essentially a proxy for communicating with the outside world, needed for security, policy enforcement, and architecture reasons. We have an adapter router which orchestrates between multiple adapters in the future. So in the future, we're also planning to have an Ethereum adapter for integration with this blockchain. And then the adapter router would orchestrate the flow here with all those adapters. So what's happening at the networking level is the following. The Bitcoin adapter asynchronously to the operation of the IC stack connects via the transit to the Bitcoin network and synchronizes the state with the Bitcoin network. So essentially it pulls Bitcoin headers and blocks and obtains a recent view of the, say, last 100 Bitcoin blocks and all the forks on there. And now let's denote this Bitcoin block here with hash X. So this is the hash X. It's relevant then for some of the things I'm explaining. And now we need to implement a protocol between the system component and Bitcoin adapter. So this protocol has two purposes. First of all, bringing transactions that should be submitted down and bringing Bitcoin blocks up. And the Bitcoin blocks that are going up will be used for building a view of the Bitcoin network also in this BTC system component. This view is also something like 100 blocks wide and contains all the forks. It's essentially a union view of all the adapters in the subnetwork because all adapters submit blocks. Now, if you look at this in a more focused way, so whenever a block is processed, what's happening is that we we extract the transactions from the block and build up a UTXO set that we keep in the replicated state. And those things are used for responding to UTXO queries. Furthermore, we keep the transactions that canisters submit in replicated state for writing it to the networking layer. Now let's focus on those two components and see how things work in a bit more detail. So as I said, transactions need to go down. Transactions then go into an output queue in the Bitcoin adapter and are asynchronously submitted quickly to the Bitcoin network. So that's rather easy. Another thing we have is this X here. It represents this block cache here. Essentially, it's all the block caches from the view of the Bitcoin blockchain that the component here has are provided down as requests. So the semantics is that the Bitcoin adapter will provide any block that builds upon one of those blocks that the BTC component has. So it's essentially a request for blocks. We'll soon see an example. So let's say the Bitcoin adapter receives a new block Y, which extends the blockchain at X, which is happening on the Bitcoin network and getting replicated here. Now this block Y is going up to the Bitcoin system component through the protocol stack. I'll show you shortly how that works. And then the block is processed by the BTC system component. So it means processed in the sense that it's validated, whether the timestamp is correct, whether the proof of work using Bitcoin semantics is correct, and whether it fits here or extends the view that the BTC system component has. And if that's the case, and if there's no competing forks, like here, then the oldest block in this view will get processed. It means that it will be consumed in our UTXO set, so all the UTXO of this block get extracted and get into this UTXO set, which we keep in replicated state. And both this UTXO set and this view are used to respond to UTXO queries by canisters. So we can give canisters all the UTXO contained here and here, so all the UTXOs that we know about, and we let them also know how many confirmations in terms of blocks on top of the transaction that each UTXO has. And using this, the canister can then easily decide whether it uses UTXO already for a transaction or it wants to wait a bit longer, like maybe it doesn't want to use a UTXO with only 1 or 2 confirmations, but wait maybe for 6 confirmations, like we usually do on the Bitcoin network. So let's now look at how this works in terms of the protocol stack integration. It's actually very simple conceptually. So let's say again, we have received at the networking level a new block Y, which extends the blockchain here after X. What's happening now, there's regular block making going on, and now we need an extension to build. So we need the block maker to pull to try to pull a Bitcoin block from the adapter router. And this one, first of all, goes to the state manager, which is now a technical issue how we implement it. So it can access the state of the BTC system component via this and pull two things, pulls down the transactions to be submitted and also these requests, so the X and all the other block hashes of the BTC system component as a request for blocks. Those two things are then given over to the Bitcoin adapter, and the Bitcoin adapter then matches the hashes with its local blockchain view, and then sees, okay, the Y again is the one that extends the view of the BTC system component, and that's why this block Y will be provided back as a response. So this block Y is now getting to the block maker. Now the block maker can, as usual, create an IC block, but this time with an additional payload, the Bitcoin block here. Now the next step is very similar as it used to be before. There's only one difference. So this Bitcoin block needs to be also validated in order to prevent that dishonest IC nodes can spam the BTC system component with maliciously grafted Bitcoin blocks. We do this by requesting a check of this block by the adapter route, and what we do is very simple. We check the block based on the hash work and based on the timestamp, and we need to do so in a way that it's the same on all the replicas, and otherwise consensus wouldn't work. And this was the tricky part, but it's a rather easy idea. I can't go into details. And all the rest now is exactly the same at this layer. So we do all the notarization in the same way, and also the finalization in the same way. So it's just 2 small extensions we did and implementing those components. And now, as a next step, as usual, the block goes out of the upper part of the protocol stack. What happens here is that it gets also inducted in the induction pool and now needs to get scheduled for execution by the BTC system component. So that's similar to execution of canister code. It's just not WASM code, but it's native code. And then the update of the view and the process of the block, as I explained before, happens and the UTXO set gets updated. And the UTXO set can now be used to respond to UTXO queries. So that was a rough overview of how it works. All the rest now of the processing works the same as usual, also the graph subnet processing. So this was the integration. It's a rather small integration surface, like mainly those two integrations here at the consensus layer and building those additional components. But the integration surface is small. Most of the code is contained in those isolated components. And there's, of course, one more thing now, threshold ECDSA. Threshold ECDSA. So threshold ECDSA itself is a huge component that cuts across the whole protocol stack. And it implements a cryptographic multi-party computation protocol, which is integrated tightly with consensus, so it has much bigger integration surface with the IC protocol stack. I won't go into any details, unfortunately, because of time reasons, but I would say the threshold ECDSA project, building this component here, it's coming up. Okay, it doesn't come. So this threshold ECDSA component is, I would say, a substantially larger project than the basic Bitcoin integration, and we are also well on the way with implementation efforts, so it will still take a little bit of time. So I hope to have shown you with a still high-level overview of how the integration of Bitcoin with the Internet Computer Stack works, and how we have a somewhat okay integration surface. And what I would like to show you next is how streamlined the developer experience is for the Internet computer when you want to do something with Bitcoin. So let's say we have Bitcoin-enabled Canister that wants to build a smart contract using Bitcoin. We have a Bitcoin library that we can run inside, so it's code running inside the Canister. We have the system component, threshold ECDSA, and we have the Bitcoin network. And now it's very easy. Let's say we build an NFT trading platform. First, we need to get the private key from the ECDSA component. Then we can bit32 derive an arbitrary number of private keys. We can derive Bitcoin addresses. We can give Bitcoin addresses in step 4 to our users. For example, every user gets their own address for transferring Bitcoin, for making purchases, NFTs. Then let's say some user wants to buy an NFT and makes a Bitcoin transaction on the Bitcoin blockchain. The block is at some point being pulled in. In step 5, we can then make a query whether the balance is already there. This is done by the library. The library would make a get UTXO set query to the BTC system component and compute the balance for us. And if the balance is okay, we can have some smart contract logic which would transfer the NFT to the buyer. And then in step 7, we would need to transfer the price that was paid for the NFT to the seller of the NFT. This can again be done with a library call, which then does all the heavy lifting. So it would receive the UTXO set from the system component, it would create the transaction, it would do the ECDSA signing, it would add the signature to the transaction, and then it would submit the transaction to the Bitcoin network. So all of this would be done behind the scenes by the library. You make a simple call in step 7 for performing a Bitcoin transaction with some parameters, and that's it. So it's a very streamlined and easy developer experience that we have here on the Internet computer to do natively integrated Bitcoin transactions, which is unique. So now this brings me already to the conclusions. I have a couple of takeaway messages I would like to convey. So the first of all is that we are now bringing powerful smart contracts for Bitcoin, which brings potentially a lot of Bitcoin liquidity to smart contracts on the Internet computer. And this is done with direct integration. Direct means no intermediaries whatsoever. No intermediaries means strong trust model, less risk that something goes wrong with intermediaries. Because there have been many cases where intermediaries like bridges have been hacked and Bitcoin or other cryptocurrencies were lost. So this is the strongest possible trust model, and it's unique in the blockchain world to do such a direct integration. No one else has been able to do this before. Next, we have a very broad support of programming languages, essentially everything that can compile to WebAssembly, and 2 languages that we support with an SDK, like Rust and Moldoko. So it's very easy for you to get started, because you probably can use a language that you know already. Next, we have a streamlined developer experience, as I showed before. Streamlined in the sense that you need to know only very few simple API calls and library calls and use those in order to transfer Bitcoin and use the Bitcoin features. And all this was done in a process of in a very decentralized way. So decentralized in the sense that we asked the community for requirements. We worked with the community on what use cases they want to do, and from this derived what we need to build. And the community voted on a proposal of building this feature. So we decentralized, or we are in the process of decentralizing the governance of the internet computer more and more by this community involvement and having a community vote on proposals of features we should do or should not do. And notably also we are doing a workshop next week with the community where we're going even further and directly working together with the community on certain aspects of this feature. Now this brings me already to an outlook. So the internet computer is evolving with a rapid pace. And our community is increasingly driving our roadmap. So this is one of our big goals, decentralization of this also. And I would like to show you now two features that are up on the roadmap that are coming. So one is at some point Ethereum integration. So Ethereum integration will allow Ethereum smart contracts to call IC smart contracts and vice versa. For example, this will allow that Ethereum can use internet computer smart contracts instead of also for serving the web page of the smart contract, because today web pages for Ethereum smart contracts are usually hosted on big text clouds, which means it's not trustworthy like blockchain. And with this integration, we could reach a state where we have everything for Ethereum smart contracts on the blockchain. But of course, there are much more ways you can use this integration for. And then there's another very interesting feature. It's the Service Nervous System, SNS. So essentially the SNS is an NNS, a network nervous system that I explained earlier for the governance in a box or in a canister that you can take, you can customize it, and you can deploy it for your decentralized app that you're building. So it means it takes decentralization one step further. So we now have 3 layers of decentralization if we deploy this. The basic first layer of decentralization is decentralized computing on the decentralized internet computer platform. The second layer of decentralization is the decentralized governance of the internet computer through the network nervous system, the NNS. And the third layer of decentralization is the governance, tokenized governance of each or of selected decentralized apps that are running on the internet computer. So it brings decentralization to the extreme level. Essentially, it's total decentralization of everything. And having this total decentralization and combining this with the limitless scalability of the internet computer, we obtain decentralized infinity. Thank you.
Wonderful, thank you all. We might have some time for a few questions. If anyone has one or two, please.
How do you select the amount of nodes that are responsible for validating a particular canister?
So the subnet selection depends on subnet types. So we can have different subnet types, and I think the smallest one is a storage subnet with 4 nodes, and the biggest one will be fiduciary grade subnet, I think, with 151 nodes, but of course it can also go further. And depending on your security requirements or decentralization requirements, you can host your canister on subnets with different number of nodes. But the important thing is that it's not just the number of nodes, but it's these 4 dimensions of decentralization I was talking about. So what we do is we algorithmically select the number of nodes that the subnet should have in a way that decentralization is the highest possible. So that's the important part. It's not a random selection, but it's really a selection that the nodes are as much decentralized as possible. So geographically distributed among different node providers, different data centers, and different legislations. And by this, we can reach a very high security. Essentially, this decentralization directly translates to security.
Yeah, but how does the network actually know what exactly I'm doing within the canister? Like, it may hold just 1 Bitcoin for me, or like 1,000 Bitcoins, and it's like totally different security requirement.
How many?
Actually know?
So if you deploy a canister, you select this. You can select subnet properties where you want to deploy the canister on. So you can say I want my canister on a small subnet or on a super large subnet. The large one will be more expensive for us.
Creator defines that.
That's creator defined, yeah.
And like in your case, I guess you're gonna.
We want larger subnets because there might be lots of value in those Bitcoin-enabled subnets. So what we suggest is to use subnets with probably something like 50 nodes or more.
Yeah, and how do you know like what is the cost of the attack on those 50 nodes? Like it becomes like
it's very difficult.
Super large, like
I mean, the cost, I don't know the economic models now, but I mean, it's a good question. Maybe we can take it offline also. But in principle, it's very hard to compromise 10, 20 completely independent entities. And of course, we can grow by having more nodes and make it as much substantially harder.
Okay. Second question.
Maybe give someone else opportunity.
Up to you guys. Okay. I have 3 of them.
I have a short question. Who runs the node?
Independent node providers.
For
So,
what reason?
so in the future, everybody will be able to do it, but they still need some work to get there.
Okay. But incentive-wise is I want to do it because it's useful to me, or
Yeah, you get revenue. So you get paid in ICP tokens. I couldn't show this model. So there's a life cycle of ICP tokens. So when you run a node, you get paid in ICP tokens. And then you can sell these ICP tokens on an exchange, or you can keep them and wait if they appreciate in value. And if you sell it on an exchange, you can get money for them. Or you can use also the ICP tokens as a canister developer to charge the canisters with cycles. So that's how you pay for the computation costs of the canisters.
How much tokens I need to pay to become a node?
So if you want to become a node provider, you need to provide node hardware, and you get tokens paid for providing the computational services.
Yeah, but I can see there's a case when we can buy some tokens. I can actually buy all tokens if the value of Bitcoin is higher than the price of tokens I get. So once I get all tokens, the price of attack is lower than the value is quoted by the network. How to protect?
So I mean, it's not easy to buy all tokens because most of the tokens are locked up in voting neurons. They're not liquid currently. So many tokens are locked up for 8 years. They're not liquid. You can't buy them in. But they are owned by independent people. Currently, it's a market cap of $8 billion. And lots of it is locked up in voting neurons and can currently even not be sold.
My question relates slightly to that. Technically, right over my head, but very interesting. You talked a lot about the decentralized nature and the community making decisions.
Yeah.
Are you saying that the more ICP that you own, the more influence you have on the protocol?
Yeah, the ICP
so it's
amount
not,
you have
so
directly translated into voting power.
Yeah. So ultimately, that's kind of like it's not ultimately democratic, is it? Basically, the richer you are, the more say you get.
Yeah, it depends. I mean, otherwise, if you don't do it like this, you can, as one person, make 10,000 neurons and have 10,000 votes, which would also not be
it's just that ultimately that skews the outcome of the project towards the favour of people who have the most money.
Yeah, they have most interest. So that the idea is that you want to evolve the network in a way that is in the interest of the network. And people who hold lots of tokens have lots of interest in the network. And it's so much decentralized there's no single parties, even not the Dfinity Foundation or the Internet Computer Association. None of them is a majority.
It's not decentralized, is it? It's very centralized. It's centralized around people who have lots of money. It's not decentralized.
No,
decentralized means it's decentralized means we're all equal, right?
No,
it's decentralized, right?
It is very decentralized. I mean,
what I'm saying is that this is a fundamental question at the heart of cryptocurrency and the heart of DeFi is like basically, is that this idea of decentralized, yeah, we love decentralized, it makes perfect sense. But ultimately we're getting away from decentralized and what we're getting is just a new version of rich people having the most say. Right? So that's why I'm just challenging you a little bit on that.
And it's an interesting discussion. Let's maybe take it offline. Yeah, it's a good discussion.
Perfect. Thank you. Thank you all so much.